Hey everybody, welcome to a True Tech live stream. I think hopefully everybody can hear me out there. Give me a thumbs up in the comments if you can, or shout something out there. January 2026, we're going to jump into talking about vacuum tonight. And I got to admit, it's kind of weird standing here in the studio again and talking to myself because I don't get a lot of visual feedback or anything else other than comments over there. Awesome. American Temperature Control. Thank you very much. Sounds great. So drop a lot of comments tonight if you have questions, have comments, want to know more about something that I'm talking about here tonight. And we're going to really try to get into some nuts and bolts of what happens during a vacuum, why we're doing that vacuum, and how to do them well out there in the field in multitude of different conditions. So let's get into this a little bit. Real quick, a lot of this stuff, pretty much everything I'm talking about tonight comes out of this book called Review of Vacuum for Service Engineers. If you haven't ever read that book, that is a fantastic book to pick up and read. Can be a little bit heavy. There is a little bit of math in there if you want to dig deep into it, but I'm going to pull some highlights out of there that are some really important things and try to show you some stuff about what's happening and how we can work around that in the field, because that's where sometimes this theory is hard to apply in the field. So I'm going to use some of my experience and a couple other things, talking to some other people and things like that to get you guys hopefully some good information. Chris Wiss is out there. Tom Huff's out there. Good evening, Huff. And Rachel Kaiser. All right. We got some people out there watching. So let's talk about connections. One of the first things we have to really consider when we are thinking about vacuum is how are we going to connect to that system and what outcome do we want? A lot of times we hear, hey, we need a great vacuum in that system. We need to pull 500 microns. We need to pull 300 microns. We need to pull 100 microns. That's great. But what a lot of people, and myself included, when I started learning how to do this, I wasn't thinking 2 to 3 steps ahead of myself. We've got to think about our connections and how, when we're done with that vacuum, when the system has that deep vacuum in it, what are the next steps that we need to take in order to maintain that vacuum and then get the refrigerant into the system without allowing any atmosphere to come into the system before we put the refrigerant in? Because remember, that vacuum is, we're just reducing the pressure in that system under atmosphere. We're taking it a lot closer to absolute zero. So the system itself now has a negative pressure with reference to atmosphere. So things can come into that if we don't pay attention to our connection. So let's switch over here. I got a whole bunch of stuff laid out on the table. We're going to talk about using some different tools, understanding our vacuum gauges. We're going to get into a little bit of talking about the sensors in these vacuum gauges and how they work and how we need to keep them safe. I got some really cool stuff on the slides here. Not a lot of slides tonight, but just a few. So let's talk about this. First thing, let's talk about core tools, right? Core tools are your best friends. Fat Boy's HVAC, just unscrew it really fast. Yeah, go ahead. I guarantee you'll get something in that system. So core tool is the minimum thing, whatever kind of core tool you want to use. There's a lot of different ones out there on the market today. Find something that's vacuum rated is what I'm saying. But what we want to do is we want to take that core and we want to remove that core out of here. We want to turn that valve off, all right? And then we're going to unscrew the stem off the back of that core tool. We're going to set that off to the side, and I'm going to take my vacuum hose, whatever kind of vacuum hose I'm using, whether I'm using, one of the black hoses here, one of these blue hoses, something along those lines. I'm going to connect that right to here, and I'm going to take that over to my vacuum pump, to one of the ports there on a vacuum pump, all right? Whatever lines up with that hose. So I want that hose going in between this side of the core tool, and that means this valve right here is now my control device. I can turn that on, I can turn that off, and the side port, whether I've got one with a valve on it or whether I've just got a regular side port here with a core in it, that is now connected to my system all the time, whether this valve is on or off. This is now connected to the system all the time on this side port. All right, so that's an important thing to remember. This allows us a place to put a vacuum gauge on that's as far away from that pump maybe as we possibly can, because the pumps are creating the low pressure point in the system, or in our system as we have it connected through hoses. So that pump is your lowest pressure point, and everything as it goes away from that pump is progressively higher and higher in pressure. It steps up higher and higher in pressure the farther we get away from that pump. So we move away from the pump, we get higher. I'm saying that a number of times here, and I know some of you are probably going, hey, be quiet, move on, let's go. But it's really important to understand. Low pressure in the pump, high pressure moving out. The farther we get that gauge, any one of these gauges away from that pump, the more accurate the measurement is of what is happening in the system. And it's in the system that we really care about getting that low pressure. And you'll see that in a couple of things I'm going to show you a little bit later. But if you have a core tool like this where you got two valves on it, okay, now I'm just moving these two valves around. I'm going to pull that core out back here. I can use these two valves, one going to a vacuum gauge, one going straight to my pump. If I'm doing something like this, I'm probably going to want to connect another piece onto the side of this, something like a core control valve. Now, this is a core control valve, and what this allows the user to do is to turn this valve in, and it moves a plunger inside of this up, and it depresses the core in a refrigeration access fitting. There's a couple of them out there on the market that also act as a valve. So when you screw this all the way back out, it turns this off right here, and we no longer have flow through this core control fitting. Now, the reason being that we want to keep oil out of our refrigerant or our vacuum sensors. And we'll talk a little bit more about that in a little bit, but we have to keep oil out of these sensors. If we get oil in these sensors, they don't read correctly any longer. Sometimes you can clean that out. Sometimes you're not going to be able to clean it out. Every manufacturer has their own directions on how to clean their sensors out. If you have a sensor you think is fouled, go find those manufacturers' directions and read them and understand how to clean those sensors up, okay? So we're going to use something like this on the side port, okay? And then we're going to tap that in. Now, if we have a vacuum gauge or probe with a female fitting onto it, we can connect that directly onto that port right there on that side port. Or if we have something that's got a male fitting on it, like this one, then we use a coupling in between the vacuum gauge and this port over here. If you don't have one of these core control valves that seals off, you can also just put another core tool onto the side port here, remove that core from the side port. You can use a second core tool on there. That works. I did that for a lot of years. There's, like I said, other ones with valves and things like that on that side port as well. So multiple different options there. But what that allows the user to do is to isolate using the side valve, using that core control valve, it allows us to isolate these gauges, the vacuum gauges, and keep that sensor clean. So if we turn that off before we go charging, then we can keep that sensor clean. Now, when we get to our desired vacuum level, one of the things we need to do is, normally we're going to have this valve turned on, vacuum flowing through here over to the pump, from the system into the pump. And say I'm at, my target is 500 microns, and I get down to 450 microns, and I say, okay, it's time to go ahead and we're going to do an isolation test on this. We're going to see how far this system rises. A lot of times we'll just reach down here and we will grab that valve, okay, and we're just going to real quickly turn it off. And that can give us a false sense of security sometimes. And this is why. So if we're looking at the inside of a ball valve, you see there's voids over here around this ball valve. And if I cycle this ball valve, all of a sudden I'm opening up this opening in that ball to all those voids around here. So what we'll end up with, if we do this real fast, we're going to end up with a quick spike on our vacuum gauge because of the proximity to this. And there's pressure, some kind of positive pressure, whether it be refrigerant or atmosphere, nitrogen, something inside and around that ball valve. So we want to take that to about a 45-degree position, and we want to watch that vacuum come up, and then we're going to watch it fall back down. Say if I'm at 450 microns and I do this, I might spike to 550, 600 microns, and then I'm going to watch it come back down under that 400 microns before I turn this off 100% and proceed with my rise test. And that way I'm not affecting that micron gauge in the same way with that little bit of pressure that was in the outside of the ball valve. So anytime you have a ball valve in any of these tools, they're going to work that same way. So you want to turn it to about 45 degrees, let it set, let it settle down, then go ahead and shut it off and proceed with your rise test. Now, if the rise test passes, everything is good, your valve is still shut off. We'll say we have a core control tool on the side, or we've got a valve on our side port here. Right now we're going to shut this valve. We've got this valve shut off. Now we're going to shut off this side valve. We're going to close that core control. We're going to isolate our micron gauge from the system that we're getting ready to charge. Now, if we're doing a new system, we may be releasing some refrigerant from, say, a condenser or something like that into that system, and that could very easily bring oil in with it. Right? Oil is definitely the enemy of these gauges. Or if we need to charge into the system, we now have a wide open path right here. There's no core right here. So we got a really wide open path. And all we need to do is bring a single hose over from our tank right into the edge of this. We can use a ball valve right here, and it will just go straight in. This is a great way to put a lot of refrigerant in really, really fast. It will put refrigerant in quicker than any other method I know other than pressurizing it and pumping it in. But if you're charging liquid in this way to get a system up to charge, be careful because you can dump a lot in there really, really quick. You'll probably surprise yourself. You may want to meter with one of these valves. And then if you want to, you can take and put a pressure gauge right on this side port here. You've got that access. And now you have a whole system where you can just put a probe on right here. It's ready to go. You've got your charging cylinder here ready to charge up. If you're doing a manifoldless setup, this is a really great way to do it, just to do it with probes. If you've got multiple ports on the system, say you have a liquid and a vapor port, you may want to put two of these core tools on, one onto each port. If you're doing a new system and it's a smaller system, one hose from here to the vacuum pump is going to work really well. And then you take that second core tool and you put that over on your other port and connect your micron gauge right to the back of it. Because then again, you're getting rid of this valve here. You're going to put a valve over here. You're going to shut this off, isolate that micron gauge before you charge anything. Okay. And you keep that micron gauge clean. And now you can connect your gauges up, your hoses up, whatever you need really fast and easily through these ports available. Once everything is all up and running, everything's on positive pressure, only then do we put these cores back in through our core tools. Once that's all up and running and operational, then we put the cores back in. That's the very last thing we do. We take those core tools off, we put our caps on, we're all said and done, and everything's working very nicely. So this is what I talk about when I say make a plan for connections. All right. We've got to think about the outcome. What are we going to end up with when we get done with this entire process? Think about this as a process. Sit there and think about with the tools that you have, every step of that process. And this was some places that I messed up really bad. I've blown up micron gauges. I've damaged the sensors in them. Not been able to get my hoses on there. I can remember the first time that I connected up a system and wasn't able to maintain that vacuum in that system because I didn't think about the process well enough. I didn't have everything connected up correctly. So by using these valves and things in there, utilizing a hose like this to do charging, the way you do this is by purging this hose really easily. You connect one end to the tank, turn your tank valve on. You have this end closed. You've got a ball valve here, and you just crack this end. Just a little bit of refrigerant coming out of it. Just enough to push the air and everything out of that hose. And while that's coming out, then you go ahead and make that connection onto your core tool, okay? And hook that all up, all right? And that purges everything out of there and forces everything out of that so that you don't have any air or anything getting in there. So, Mechanical Environments in the chat. Welcome in tonight, all the way from Colorado. Thanks for joining. Let's see. Now, let's get into what do we got up next here? So, we're going to move on from connecting, and that's really think about that process as you're going through. Think about it before you start connecting up. How are you going to get that charge into that system without ever opening it to atmosphere while it's under a vacuum? And if you think about that, you set that up, you're going to be successful in having that vacuum remain in the system throughout the process until you put refrigerant in there. All right. Oh, yeah, this is a fun topic. Nitrogen. Was talking to a friend of mine, Roman Baugh, down in Florida recently, and nitrogen came up and the topic of water in nitrogen. Now, a lot of times we think about nitrogen as absorbing moisture when we put it into the systems. I'm sorry to burst that bubble. Nitrogen does not absorb moisture. Nitrogen can push moisture out. Okay, nitrogen can push it out by velocity. The moisture, the water vapor inside of a system, if there's any in there, is not going to chemically attach or molecularly attach to that nitrogen. That nitrogen is not going to carry it out. And the nitrogen that we get, right? Nitrogen that we get in standard nitrogen tanks, this, if you read this tag right up here, is going to say compressed nitrogen. What does that mean? That means that it is not truly dry. A lot of times we think of nitrogen as dry. Nitrogen in these tanks, the compressed nitrogen, actually does have a moisture content to it, and it's allowable moisture content. And a lot of times these tanks go over that moisture content at times. I was talking to, again, some friends that they're finding moisture in a lot of nitrogen tanks. And so we talked through a couple things. And it's a challenge to deal with. Let's discuss a couple things here. First off, I'll grab that nitrogen tank again. These don't have dip tubes in them, okay? So sitting upright, if there's any water, any liquid water, it's going to sit down here. If you get one of these tanks and you want to find out if it has moisture in it, tip it upside down. I don't recommend doing it with just a live tank. I would put a regulator on here. But you can do it with a live tank if you can hold on to it. That's up to you. I recommend putting a regulator on there first. You may want to tip this nitrogen tank upside down and find out if it's got water in it, because that water is going to drain to that valve and come out through that valve. So that can be a challenge, especially if you're getting a lot of it in your area. Some people are literally just setting that tank upright and not disturbing the liquid water on the bottom of it, dealing with any water vapor that comes out with that nitrogen and pulling that out with a vacuum pump. So that's a couple of things that we can watch out for. If you want to test and see how much water vapor is coming out, if it's enough to soak something, throw that regulator on there, put your hose on and blow that hose onto like a white paper towel or a blue paper towel, something clean that you can visibly see change color when you see that moisture come out and hit that towel. Froggy Beluga, displaces. Yes, thank you. Great term. Awesome. Thank you very much. So that nitrogen would displace moisture by forcing it out, or the velocity carrying it out. Now, one of the concerns we have also is dealing with cold weather. A lot of times we're seeing a lot more things like heat pumps going in, even air conditioners getting put in cold weather. And that can be a concern. One advantage of cold weather is that nitrogen tank right here, if this is below freezing, if there's any liquid moisture in it, it's solid moisture now. And hopefully you stored that upright so that it's all down here. And it doesn't do something weird on your truck or get into that valve or something else as liquid water. One of the tips I can give you on these tanks, and I've seen people do this before, where they get done with a job and they're going to blow all the nitrogen pressure out of that tank because the statement that's been made to me is, hey, I paid for that nitrogen, I'm not going to give it to someone else. Well, if you ever look at where these tanks are stored and how they're transported, a lot of times when they're on the cylinder trucks, not in our distributor trucks, but in the cylinder trucks, they're open air. They're stored outside. So if you crack that valve all the way open, let that nitrogen off and leave that valve open, guess what? Now water can just get in there. Water vapor, liquid water, whatever. So leave some pressure in those tanks. It's advantageous to you to leave a little bit of pressure. Use what you can, but leave a positive pressure in those tanks, because it's going to be better. Leave the valve tightly closed and send it back to the distributor that way. Send it back to your gas supplier that way. You're going to keep those tanks cleaner over time by doing that. All right. Now let's get into, let's see, where are we at? Oh yeah, now we're getting into some fun stuff here. Let's talk about vacuum gauges a little bit. So vacuum sensors in any vacuum gauge that we use in the field today is going to be one of two types, and most of them are a thermocouple type sensor. The other type is a Pirani sensor. I know there's a couple of them, a couple of manufacturers out there making Piranis, but typically the thermocouples are less expensive to make. They have equal accuracy, and the thermocouple sensors tend to be a lot more durable. Some type of a thermosensor, which means that these gauges are not a pressure sensor. They are a temperature sensor. So not a pressure sensor, even though they're reading a pressure on the display, we're reading a pressure above absolute zero in microns. They are a temperature sensor. Now, the way this works is that these sensors are generally calibrated to nitrogen or air, very, very similar. And we'll see a little bit more about that later in another slide. But that means that we can easily contaminate them with things like oil because they're a temperature sensor. And what it's looking for is in a nitrogen, an almost pure nitrogen environment, that sensor gives off a certain amount of heat. And as we reduce the number of molecules around that sensor by pulling our vacuum, that sensor cannot release its heat anymore and it gets trapped in there. Okay. And it can't transfer the heat away. So there's a difference in the way that the sensor reads if we get something contaminated on it. So just keep that in mind. Now, let's switch. Whoops, I'm going the wrong way here. Let's switch over to a little bit different view, and we're going to look at this chart real quick. I hope you all can see this. If not, look it up in the review of vacuum book, and I think you'll be able to find it in there really easily. But this chart talks about vapor pressure and specific volume of water versus temperature. So let's dig into this a little bit. So we're talking about the vapor pressure of water on this curve right here. On this side, we're going to talk about millimeters of mercury, and 0.500 millimeters of mercury is 500 microns. So 1.000 millimeter of mercury is 1,000 microns, and so on and so forth. That's how the scale works. So that we actually read this in pressure of millimeters of mercury is how we're using this scale. We call it microns because we want to read all the way out here to the thousands column. All right. So let's take a look at what happens as we reduce the pressure. What happens to that vapor pressure? Okay. So we come down here, we're going to keep reducing it down. And if we look down here, this is a temperature scale. It goes all from 80 to negative 60 Fahrenheit across the bottom. So if we look at 32 degrees Fahrenheit, we follow this line up and we intersect with our vapor pressure line. We're going to be just a little under 5,000 microns. I think it's about 4,580 microns, something like that. And that's where we talk about the triple point of water. Okay. Now, the triple point of water is where we lose one phase. So normally we have vapor, we have liquid, and we have solid. Now, at the triple point, we lose our vapor phase. We're going to take that away, and we're only going to end up with two. So we have vapor and we have solid. Keep that in mind. Because if we reduce that under that point, under the 4,500 and change microns, I tend to call it 5,000 microns because it sticks better in my head. And I think about it that way. And I'll talk to you about why here in just a second. Our vapor pressure goes lower than 32, and we can start to freeze any liquid water in there. If the water's vapor, we're fine. But if you have liquid water in the system and you get down to that point, if we don't have enough heat transferring in through whatever that water is in contact with, because it may be in contact with like copper or aluminum or something like that, that's got heat on the outside of it and can transfer it in. If we still have liquid water as we're going down, once we get past that point, we risk changing that water into ice. Okay. And that water then changes into solid. And the only way that we can convert that water from solid back to liquid or vapor is by adding heat to it. We can reduce the pressure on top of it, and that will sublimate from a solid to a vapor. But that takes a long, long time to do, especially if we don't add any heat. So be very careful of that. If you know you've got liquid water in a system and you're going to try to pull it out with vacuum, if you don't have any other way to pull it out and you're going to try to pull it out with vacuum, keep your pressure above 5,000 microns. Set up some kind of an automatic system to where it automatically shuts off if it goes below 5,000 microns. Do something, maybe restrict it with a smaller hose. Do something so that system doesn't fall under that 5,000 microns until you bit that water out. Now, another way to help get water out is to add heat into the system. Put that heat in there. Get that heat going in. to wherever that liquid water's sitting at. I hope you never have to pull liquid water out of a system with a vacuum pump. Don't recommend it. It takes a lot of oil, a lot of patience, and a lot of time. Highly recommend getting the liquid water out some other way and then using the vacuum pump just to pull the vapor out. But in the extreme case that you might have to do that, that's some considerations to make right there. Okay. Now, we also have to worry about this if we're dealing with cold weather. A lot of us deal with cold weather outside. We're trying to put things in the wintertime. And if it's below 32 degrees, there's a good chance if there was any liquid water, then you're already going to have it turned into solid. Let's see, we got a comment here. Froggy Beluga. Blow through with nitro. Blowing through it with nitro is only going to force it can help force liquid water out. Yes, you're absolutely right, because it's gonna help force that. It'll carry that liquid water out. Probably won't get rid of 100% of it because you're gonna get droplets stuck on the inside of that tubing. Now, the advantage to that is that now you have droplets everywhere rather than a puddle sitting in the bottom. So your volume of water in one place is much smaller, which means that the heat from the tubing can transfer into each one of those droplets much quicker because you have a much smaller amount of water. It'll vaporize much faster. Okay. Yes, John, thank you. Nitrogen does have moisture in it. We discussed that a little bit ago if you just came in late. So you can go back and watch that. We talked about it. So typically nitrogen doesn't have any liquid in it. That is a special thing that does come in some nitrogen tanks. But all of it does have some moisture to it, hopefully not much. Now, if we're dealing with cold weather, you got to think about the scenario. What are you doing? Do you have 3 foot of line set outside and everything else is in a warmer house or a warmer building? Or are you dealing with 100% of your system in that below freezing weather? Does the house not have conditioning? Does the building not have conditioning? We got to think about what's in that sub-freezing weather to kind of make our next decisions. Because we want that system to be above freezing. We want it to stay above freezing the whole time. It's better even to add heat to it because that's going to kind of excite any molecules in there and allow that to sweep out through the vacuum pump. I see you there, John. Thanks. Appreciate you. So if we're below that pressure or below this temperature point here of 32 degrees, that water's already going to be solid if it is liquid. If it's vapor, it's just going to be vapor in there, and we're still going to be able to pull it out. We don't freeze water vapor. We don't turn that to ice. We've got to have liquid water in order to turn that into ice. That's this way, okay? So if we look down here at 500 microns, 500 microns carries down to about -12, maybe -13 degrees Fahrenheit. All right. That's not real great if we're operating a heat pump, because if we do actually have a little bit of water in there, okay, there's a chance that water can start freezing at our outdoor metering device, because our outdoor metering device on heat pumps is going to hit that -12 Fahrenheit somewhere around probably a positive 12 degrees Fahrenheit, maybe positive 12 to 15 degrees Fahrenheit is where that metering device might hit this point. And if there is any water in there, it can start freezing in that metering device. So we may need to pull, down here to this 100 or even sub 100. If we get down to 100 microns, we're looking at -40, right? That's where Fahrenheit and Celsius meet, is at -40. All right. If we get that system down to 50 microns, we're at -50 Fahrenheit. Chances of our metering devices running, our metering devices getting this cold are pretty slim. It could happen, but it's going to be pretty slim because of the way the refrigerant systems work and injection and things like that, even on super low temperature heat pumps. So on low temperature heat pumps, yeah, it's probably a great idea to get down to that 100 microns in the system if you can. That's going to be a really hard thing to do in the if you're working in cold weather. I highly recommend putting those in warmer weather. But sometimes we got to do what we got to do, depending on what the customer needs and how fast they need heat and things like that. Okay. Let's talk about this a little bit differently, though, because some of this goes into things like dryer sizing. How much moisture do we actually have left in there? And we see a lot of dryers sized in tonnage and things like that, but they're actually really sized in droplets of water. So if you look at charts, and there's this other chart in here in the review of vacuum that shows in grains of moisture, okay? So we're going to talk about parts per million up top, parts per million versus pressure. So if we get down to 500 microns, our maximum parts per million is going to be about 400 parts per million of moisture per cubic foot. Okay. Or I'm sorry, parts per million. So that's not per cubic foot. Grains of moisture, we have grains of moisture per cubic foot of dry air over here. So if we get our 500 microns and we follow that over here, we're going to look at maybe 2.6, 2.7 grains of moisture per cubic foot. All right. All right. We have grains of moisture per pound of dry air over here as well. So there's a couple different scales in there depending on how you want to convert it. But I'm going to show you a neat thing on the next slide. So this is a little bit more about using some of these charts inside that review of vacuum. Now, 1 pound of water is equal to about 7,000 grains of moisture. We talk about grains of moisture when we're talking about relative humidity in spaces, absolute humidity, and things like that. 0.77 grains of moisture equals 1 drop of water. So 1 drop of water has about 0.77 grains of moisture in it. So you can use this chart to accurately size filter dryers once you know that other piece of information. Okay. No questions on that so far? Come on, you guys. If you guys have got questions, let's pop them in there. All right. Let's have some fun. So this is where we're talking about vacuum gauge sensors, okay? We're talking about these sensors in these vacuum gauges again. Why do we need to keep oil out of them? And what's something that can cause strange readings in our vacuum gauges? Well, let's look down this chart. So this is a chart of thermal conductivity, okay? It's based in watts per meter Kelvin. We got Fahrenheit over here. Sorry, I had to blow this up. It's not super clear. Let's see if I can get a different view here on it, and maybe that'll make it a little bit easier to see for everybody. We've got temperature over here of the gas at whatever point it was shown, all right? And we're showing whether it's gaseous or liquid on this side. So if we're talking about argon, now I put argon on here because argon is a really common gas that a lot of us are familiar with, whether we know it or not, because it's very common in windows, especially in double pane, triple pane windows. They'll use argon in between those panes of glass because it's fairly common, okay? and it has a pretty low thermal conductivity of 0.016. We're just going to use that kind of as a reference. All right, let's see. We got a question over here. No questions. Leave the psychometrics outside the copper. Unfortunately, the psychometrics happen inside the copper as well. So, but I appreciate you commenting there. Nitrogen. Okay, this is where a lot of our micron gauges, most of them are going to be calibrated either nitrogen or air, but a lot of them are done to nitrogen because we use that nitrogen as our pressure test gas. So it makes sense that we want to measure that in a almost 100% nitrogen environment or a nitrogen-rich environment. That is a 0.024. All right, air, as we can see, standard air at sea level, zero humidity, 0.0257, standard air at sea level, but we added 50% relative humidity in there as a 0.027. So really actually pretty close to our nitrogen. And oddly enough, air is mostly made up of nitrogen. So that kind of tracks when we think about it. Here's where things get interesting. Refrigerant, if we have refrigerant present in a system, say we're doing a repair system, and we have oil in that system that is coming out and it's releasing, it's been entrained in the oil, maybe sitting in the compressor, and now it's coming out because we're reducing that pressure up above it even farther. It's coming up out of that oil. It's releasing from the oil. It's releasing from the oil that's attached to the walls of the system, wherever. Okay, and it's getting into our micron gauge. We have no idea about what concentration of refrigerant versus nitrogen we're getting into that gauge. But if we sweep with nitrogen, suddenly our gauge comes down and falls in line with what we expect for pressure. This is because we took the refrigerant out. I threw a couple different types of refrigerant in here, right? So R410A has a much higher thermal conductivity, all right? So remember I said those sensors look for insulation around them. So as we remove, first off, nitrogen's got lower thermal conductivity, and as we remove those nitrogen molecules, it's going to conduct less heat away from that, so the sensor is going to stay hotter. R410A's got higher thermal conductivity anyway. It's like R32 down here. So when we end up with refrigerant in there, it's going to give us a false high reading. Everybody getting that? So refrigerant in there is going to give us a false high pressure reading. The actual pressure could be much lower, but because we're designed to measure at this nitrogen or air range here, getting a false reading. So we got to get that refrigerant out of there. We want that to be 100% nitrogen environment, even though we're pulling a lot of those nitrogen molecules out of there. Like if we take it from atmosphere, if we look at a molecular count, if we take it from atmosphere down to 500 microns, and we say atmosphere is 100%, at 500 microns, all that's left is I think it's 0.06 and change percent nitrogen in there. So we're reducing the number of molecules a lot, but there's still a little bit in there, and that would be the primary molecule that the sensor is going to see inside that system is nitrogen. So if we mix a little refrigerant in there, we can change how that reads. We need to get that refrigerant out. So best practices are to help do that are going to be on repairs. This is especially important on repairs. Try to heat that oil up if you can to help get the refrigerant out of it, and your vacuum will actually be more accurate when you're bringing it down. It'll come down faster so that you can get push that refrigerant out. And if you're coming down on a vacuum and you're watching it and suddenly it stalls out, there's a good possibility that's not actually moisture in the system. It's actually refrigerant off-gassing, and it's put in a refrigerant-rich environment in there. Stop it, sweep through with some nitrogen, and see if it comes down real quick. You don't have to do a big pressure test. It just needs to be a sweep, push through of nitrogen, That way you end up displacing and pushing that refrigerant out the other side, and you're making that a nitrogen rich environment again, and see if that nitrogen level comes down. If that the nitrogen level, if the vacuum level comes down immediately after doing a sweep like that, you had a refrigerant rich environment in there. Now you're going to be able to get a better reading on that vacuum gauge. All right. And if we look down here at the bottom, we can see if we get that refrigerant oil on that gauge, we could get some pretty bad stuff happening. And the challenge is that refrigerant oil is liquid, right? So the liquid getting on those sensors is drastically going to affect that, where the gaseous stuff is going to come off those sensors really easily. So if we get that liquid refrigerant oil on there, this is where we have to keep these sensors free of refrigerant oil, okay? None of them like refrigerant oil. Some of them have filters and things in there to help get from getting the oil and stuff up inside of that. I've seen the oil get past all of them. Right? It's the number one killer of micron gauges is refrigerant oil. I don't care what kind of micron gauge it is. Keep the oil out of it. It will last you a lot longer. It'll be a lot more accurate. All right. So when we're talking about making that plan with all of your fittings, right? Anytime you got these fittings, make that plan so that when you go to charge, you're going to isolate that gauge, keep the oil out of it. Keep the oil out of it. Okay? Get the oil away from these gauges. They'll last a long time for you. Okay. No questions? I tried to leave time for questions in here, and so you guys wouldn't have to stick around all night and listen to me talk, but let's see what we got. We'll wait a couple seconds. All right, John Whitehead, thank you very much. Makes a lot of sense and explains a ton about our past questions and mistakes. Well, I won't say mistakes, John. I'll just say you had gone through a learning experience, and I think all of us have. While this information's been around for a long time in the Review of Vacuum book, it's not necessarily been, for years at least when I came in, wide knowledge. And I still see a lot of places where it's not taught real well. So thank you very much for that comment. I really appreciate that. I do want to tell everybody that if you haven't heard about it already, if you need to get a hold of us, you can do it at TrueTechTools.com, or we now have a TrueTech Tools app, which can be found on the Play Store and the App Store. And yes, the vacuum book can be had at either one of those places. Thank you, Mr. Bill Spohn, for dropping in and saying hello to me. Always good to see the boss on. So if we don't have any questions, I'm going to go ahead and call this out. So if you guys have anything else, we ruin gauges and blame the gauges. Yes, John Whitehead, that happens a lot, unfortunately. I have talked to people that have done this exact same thing for a lot of years, and it's almost always the gauge's fault. Okay? So just trying to help you out there, and that way you don't have to deal with thank you very much, John. Appreciate that. Don't have to deal with the problems out in the field as much. You know, to me, once I learned that, and I figured out why I was having problems with micron gauges, it was a game changer for me, because then I didn't have to worry about keeping extra micron gauges on a truck or saying, oh, do I really believe the accuracy in this? Is it telling me something that's right? You know, and it was a very big aha moment when I hit that. So, all right, folks, if you don't have any questions, thank you very much for attending tonight. And we'll see if we can have a few more good live streams this year and get any questions you got. If you do have questions, feel free to reach out to me, reach out to our team, our customer service team. They're really great, and I'll be all over social media. So if you need anything, Huff, thank you very much for showing up. Oh, Froggy Beluga, great, great question. To verify the gauge connect directly to the pump. Yes and no. That's actually a really great way to verify your pump is working. The challenge there is that you don't know what that pump is actually producing. So if you don't know what the pump is producing, it's not a great way to check a gauge. You can take two gauges and put them side by side, and a lot of them will be somewhat close, but you're going to see some differential between gauges. This is the nature of any kind of measurement instrument. We're probably going to see differential between those two. They should be pretty close. Mechanical environments. Been pulling vacs with 2-micron gauges, one on each sear. I'm just going to add that to the show here. All right. They both agree something is up, then it's a real problem. If only one is acting, that's likely an issue with just one. That's probably a pretty good way to do it. It's a great way to check each other. Now, you can also use a micron gauge to check your pump. If you hook that micron gauge directly to your pump, you should be able to pull somewhere close with fresh oil in it. You should be able to pull somewhere close to its rating, whatever that rating is. I generally tell people if you can get under 50 microns in a fairly short period of time, like less than a couple minutes, your pump and your oil are good. If you can't do that, if you can't get down that low under that 50 micron fairly quickly, first thing you want to do is change your oil. All right, change that oil. That oil is what keeps the seal inside the pump. So, yeah, that's a great thing to do there, Megan. All right, everybody. I appreciate you coming out and spending a little time with me this evening. Hopefully, like I said, some great comments in here. People said it sounds like really good information. And hopefully that helps everybody out and everybody else that watches this video later on. So we will talk to everybody on the next one.